All right, so welcome to this session where we're going to talk about our resources. So this is work joint with Rich, who you can see there, and also who is off someplace and off my screen here at the moment, who's helping us out in background here. And what we do is we have written four books for Make so far, three specific math books, about which more in a minute, and a new book that is a teacher's guide to the other three, sort of talking about how to teach it. And so we'll talk about how that's been going. And I always mention a grant that we had to do some of the early work in this space, about which more again in a minute. So the two of us have been partners for 10 years now. And we've written a pile, literally a pile of books at this point. So all the books are on the left there. Rich came into this as a 3D printer developer in his misspent youth there. And he developed some of the earliest RepRap open source 3D printers, including in his, let's see, right hand, the Paquito, which was a commercial printer, which unfortunately got copied by a company that could make it much cheaper than us. So we had to do something else. So we started doing training. So you can see us at Bay Area 2023 there with all our stuff. We also have done LinkedIn learning courses and a lot of other things um, along the way. So what we tried to do is use the principle of universal design. Very early on, we had a lot of interest from the blind community in our 3D printed math models. And I'm going to be showing some of the models and how we developed them shortly. And so we said, well, here's this interesting edge case, which is what the grant was. How can you do math visualizations for somebody who can't see anything at all? And if you go all pure tactile, then you have to think a little bit differently. And it's turned out that making those accessible has also been very powerful for people who maybe want to learn math a little bit differently or who aren't prepared or whatever else, however else you want to put it. I'm going to pin myself here so that you don't all feel like you have to be on screen. Whoops. So our models are written in an open source CAD program called OpenSCAD. I don't know how many of you have seen that. It's a free program, and it's an open source constructive geometry program, and I will do a brief demo of it in a sec. But the models are coded as opposed to drag and drop, which is good and bad depending on your like of such things. In a language that sort of looks like C or Java or Python or something. It's a very good way to motivate learning programming too, by the way. You can download it at openscad.org. It runs on all the common platforms. There are block versions of it, but they're kind of subsets, and so they don't really line up with our models very well. And some of the beauty of a CAD program that generates, text code files is that you can have your models on GitHub and manage them as code. And so we have repositories of about 100 models now, covering a lot of science and mathematical topics. They're all CC BY, freely available, and described in our books. And also as a side benefit, this is one of our blind colleagues using one of our models. OpenSCAD also has a text-only command line interface, and so visually impaired designers can also uh, use our models, modify them, print out the result, and they can have a design cycle where they can actually see this. So that's kind of a very powerful thing. And so this is what OpenSCAD looks like. And I'm going to stop here and actually do a little demo in OpenSCAD. So let me open that. If you bear with me for a minute. Multi project extravaganza here. Okay. So here we have OpenSCAD. So here I have how OpenSCAD has you write a rectangular solid. So everything's a cube, and technically it's not a cube, but I can render that and poof, I have a cube. So it's really good for mathematical models. And I can take that cube, I cheated and drew things in a comment here so I could add them. Now suppose I want to move that cube, I can move it. This also lets you teach things like translate and rotate. There's translate and rotate and all that sort of stuff. So kids can get in here and play with it. We teach and we pilot a lot of our stuff at a wonderful enrichment after-school program called Institute for Educational Advancement in Pasadena. And so we've had kids as young as about 9 or 10 can handle OpenSCAD. Um, they like to make it blow up, which is kind of a little annoying, but that's just how kids are, right? Um, if I want to add a cylinder to that, I can add a cylinder to that. If I want instead to subtract a cylinder from a cube and have negative space, I can do that. So all the kinds of things you would kind of anticipate. You know, if I want to see how they intersect, I can do that. What happened? Oh, intersection. Oops. This is what I get for not copying my prefab thing. Okay, there we go. So you get the idea. And it's a very powerful language. It's documented beautifully on their site. They have some of the best, really nice cheat sheets and documentation I've ever seen. Um, and uh, and you can get the general idea from that. So let me stop sharing. And I'll show you some of our models when we get a little bit farther along. Let me go back to my slides here. Okay. So we just saw OpenSCAD there. So we started off with some science projects. The original science projects book was written in 2016. We've heavily updated it. That just came out. And there's also a second volume. The volume one is kind of middle school to high school kind of topics, and I'll show some of them. The volume two is skews a little bit older, a little bit more engineering. That's a probability model. Um, so here's a couple of the models from science projects. I'm mostly going to focus on the math, but just to give you the general idea. So for instance, in OpenSCAD, these models of camellias and agaves are the same model as each other in OpenSCAD. They're printed without support. All our models are designed so that they'll print on a beat up, sad and crappy printer at a school because we know what those printers look like because we consult for schools. And memorably, somebody had a printer sitting on top of a lathe completely covered in wood dust, and they said, it worked for a while really well, and then it hasn't worked lately. So we know what it's like at a school. So we try to make these things, as robust as we can. So those models are a Fibonacci number worth of petals laid out at the golden angle, and that's kind of a fundamental that not every plant follows, but many do. And so you can have kids design alien plants and think about the plants and think about the botany, and you can teach botany that way. The other picture here are our wings. So those are accurate World War II airfoils. That is an OpenSCAD model, and you can ask it to make a NACA airfoil. These are a lot of classic airfoils. That's our non-scriptum. Non-scriptum's our company. We call this the non-scriptum Air Force here. And so you can tilt them at different angles to have different angles of attack, either climbing or on the level. And then you put them on a postal scale. Rich is there is showing having them on a postal scale and put a fan on them. When you blow a fan on them, they generate lift, and you can measure the lift. And so we have found really nice old graphs of early wind tunnel tests of these things in World War II, and we have some links in the book to those. And you can see if you get what you're supposed to get, and kids really find this fascinating. And the little tray on the bottom is because they have enough lift to take off, and so you have to kind of weight them down with a bunch of pennies so that they don't do that. But anyway, they are accurate World War II airfoils, and we had to go back to a report signed off by Wilbur Wright to get all the parameters we needed because people have just been passing around these things as more sophisticated CAD for a while. And there's a whole funny side story there if we ever meet up and have a beverage. But anyway, so people said, well, that's pretty great. And there's sort of these topics, we picked topics that lent themselves to this, and our blind users loved it. But somebody said, it would be really nice if you could attack trying to teach a subject end to end, particularly math, and apply your universal design to doing that with 3D printable models, but also some other hands-on activities. So, Dale and Make have been wonderful supporters of us. The geometry book came out first, the calculus book, and then Trig. And we also have the teacher's guide, but more about that. So to give you an idea, I'm going to show you basically a couple of models from each book. We call them math experiments because math should have experiments. Science has experiments, right? So why can't math have experiments? And we try to teach geometry and intuition first and applications and then feed the algebra after that. So doing that, we've taught calculus concepts to kids who are 9 and 10 years old, and they are then real super motivated and they have attitude in their math classes because they know a little calculus now, right? And so it's very motivating. So I'm going to stop sharing for a minute, and I'm pinned for everybody, right, Rich?
No,
Hopefully. Am
no
I?
pinning is only for your screen.
Okay, can you, if I remove the pin here, can you pin for everybody?
Spotlight isn't, I don't have a spotlight option. It
Okay,
just
well,
doesn't
let's see
work.
if I can do this. Let's
If
see.
you do it as a share screen, it should show up on the recording properly.
Well, you guys can each pin for yourselves. That you go up to the little corner, you can try to do that. So I don't want to mess with cameras right now. But anyway, so here's some of our models. So you probably all at some point made paper versions of a model to make a cube, right? And they're really annoying to use. So Rich is great insight. Rich designed our models, and somebody walked off with our good one. Unfortunately, we discovered. So this is a little bit ratty. So what Rich's great insight was to say, well, what happens if you fill the space inside instead? So this model completely fills the space inside the cube, and so you can hand this to a kid and say, what's the volume of a pyramid? And they can fairly rapidly deduce that, oh, well, it's 1/6. They can get to Cavalari's principle fairly quickly. Um, and you can do a lot of very interesting reasoning about this, even with a blind kid. A blind kid, it's completely hopeless to try to make one of these, right? But you can hand them to them, they can do this and they can explore it. Um, One of the things you learn quickly with working with blind students is they need to have a starting and end point in the model, a story behind the model. And needing that premise really helps you, with all students to feed you this model. So this is a relatively short OpenSCAD model. We have time. I'll show it a little bit at the end. Um, but the beauty is that this model has a parameter in it, which is a number of sides. So you can do all the platonic solids with this model. So, for instance, this is a dodecahedron, and you can just fold it up like that. If you've ever made a dodecahedron net, you know that they're unbelievably annoying. So this is a really much better way to do it. These are printed in TPU, by the way. You can print them in PLA, but we do a lot of shows, and people do things like hit their sister with it at our shows and stuff, and so they don't survive. And so they're very powerful. And here's the octahedron. And so, you can just do that, and it's very motivating. And we have kids play with them, and I end up giving a lot of them away to blind people because they don't want to give them back because you get so much insight from this that you can't get any other way, really, from doing that. So geometry has lots of models and lots of projects. Well, my favorite project in geometry is you can figure out from a handful of measurements what your latitude and longitude is, and that's very empowering. People really get excited that you can do that. And you can do that with, pretty little kids. You have to teach them basics of sine and cosine, which you can do with this. So this model is a right triangle, which has a hypotenuse, which is 1 in some units. And therefore, the sine of this angle is opposite over hypotenuse, which is 1. So therefore, I can just read off with a finger or by counting the sine on this side and the cosine on this side. So as you change the angle, you can see how the sine and cosine vary. I've had pilots frighteningly want this to calculate crosswinds because they can feel it. And I find that oddly disturbing. But anyway, it was designed for a blind user to be able to do with a finger. And this model has excited a lot of people because it really helps you think about, well, okay, so as the angle changes, where can I get to the sine and cosine being equal to each other, for instance? And this tactileness really helps make it very real. And so you can teach pretty young kids enough trigonometry they can go out and figure out their latitude and longitude without breaking too much of a sweat. Another fun one is this is a unit circle model. And if you haven't, let's just see how this will work. But anyway, I have an x-axis and a y-axis, and I'm graphing, let's see, this is sine 2x. So sine 2x starts out at 0, goes up to 1, goes back to 0, goes down to 2, goes down to -1 and goes around twice, right? And so this is a 3D graph of sine, and that's mildly interesting. You say, why would you bother? Well, what you can do is you can take this extremely high-tech device, which is one of these things that you can draw on, and you take this model, and you're not going to be able to see me do it at this angle, but I can roll it out. We on the cover of the book, we did this with Play-Doh. I can roll it out, and rolling it out gives me a sine wave. And so this is a way of seeing in a very tactile way that you can create a sine wave. And pretty little kids will stand around at our booth and do this for very long periods of time. We have a bunch of these. So the model lets you do any trigonometric function. We have tangent, which you have to cut off because it goes infinite. We have tangent models that are just a little bit longer. You can do this with a toilet paper tube, but it requires more patience than I have. But you can do that. But it's a lot funner here because you also have the division, so it's a little hard to see on this, but you have some fiducial marks that you get when you roll it across, and that's really helpful. And then of course they get interested in this and want to draw on it, but that's another whole thing. So our calculus book starts with Legos. Now, I don't know how many of you have taken calculus, but I'll try to do this quickly here. Here I have the curve x squared. This is just in standard Lego bricks. So my x squared is 0, 1, 4, 9, and 16. Okay, and so calculus is all about how things move and change. So I want to know how this is changing. So I'm going to ask, what's the difference between these two columns? Why, it's 7. So I'm going to put a 7 in between those two. Whoops. It's just a super good Lego here, but I'm going to fill it in. And the difference between these two is 5. So I'm going to put that in between them. And the difference between these two is 3. I'll put that here. The difference between 0 and 1 is 1. So I'm going to put that here. So now I have a curve x squared, and I have a curve of differences. And so my curve of differences, oh, look, it's a line that goes up by 2 each time. So my derivative, as it's called, my curve of differences for x squared is 2x. And so it's really, a really straightforward way of giving people some intuition about how that works. And if you haven't taken calculus, a derivative is sort of a generalized slope. It's we want to see how something is changing, and we walk through that. And there's a lot of huge amounts of algebra to do that, but you can do it more simply. You can also do another proof, something called the fundamental theorem of calculus, which says if I add up, otherwise known as integrating, all the area under this curve, I should get the original curve back. And so I can prove that by saying I add up 0 and 1, I get 1. So I get this one back. I add that, my 3 to my 1, I get my 4 back on the original curve. I add that here, I get this. And I add this one here, and I get back my 16. And so fundamental theorem of calculus. So that's first and second semester calculus with a little handful of Legos. And you'll say, well, but what about continuous? So then what we do is we have 3D prints, and we have an OpenSCAD model that here's my x squared scaled to the Legos so that you can scaffold directly from it. And here's my 2x, my curve of difference is my derivative. And so we moved to a model, um, where we can talk about if I have my derivative, I can integrate to get my original curve back. If I have a curve and want to take its derivative, I go this way. And so we can have this physical formalism of going back and forth between them. And the model also is designed so that you can put in an original curve and tell it what you think the derivative is in OpenSCAD. And then you can put in what you think it is, and it will calculate numerically what it should be. And so you can see if you're off. So it's kind of a nice one side effect is that the model has a little bit of a tool to let you do that. What's really fun is if I have a sine wave, its derivative, its slopes are cosine, whose derivative is minus sine, whose derivative is minus cosine, I can go the other way to integrate. So, it's a very powerful tool. We have a little class of 9 and 10-year-olds, and so we walked through this with them, and one of them came up with the fundamental theorem of calculus by just sitting there and looking at it, which kind of made me depressed in a way. But because I'm glad I don't have to compete with him for jobs. But anyway, all right. So back to my slides. I'm going to try to leave a little space at the end so we can talk about it, please, a little bit. All right. So all our models are on GitHub. There's a repository for each book. If you go to our main website, Rich, maybe you can type our website in the chat. The websites are all the repos are linked at the bottom of nonscriptum.com. Of course, we prefer that you buy our books and see how to use them because that's how we make our living. But those are there and they are CC BY, so you can print them. You can do whatever you want. You just have to attribute our books when you do that. And it's in 5 repos because it's two science books and then it's the 3 so far math books. So the barrier has been people said, we put these books out. Excuse me, and people have said, well, that's fine, but we're not you, so how do we do this? And how do we think about this? And, so we had a lot of conversations with Make, and we decided to write this most recent book that we put out, which is a skinny little book, but it's a teacher supplement, and you'll see throughout kids' hands, and these are kids we've actually taught the content that we're talking about in the books, and they are 9 and 10, respectively, or they were at the time. They're a year older now and too cool for any of this. But we thought about what does it mean to show your work if you're teaching people like this? How does that work? We've spent a lot of time thinking about that. It means something somewhat different. We've how do you scale showing your work if you're teaching like this? I mean, a worksheet has evolved because it's easy to grade and it's easy to hand out 30 of them and take them back, right? But how do you do that? And so the short answer is that you have to find some way for them to show you some variation on what you've done and spit it back at you that way, or to intelligently alter what you're doing so that they can show it. We've discovered a lot of teachers, I'm sure not this crowd because you're Fab Lab people, but a lot of teachers are afraid of the tech and of OpenSCAD and, oh my God, it's coding, we're all going to die. Not so much math faculty, although occasionally. And so we have a longer background section on some of the technologies. And then we have a list of topics arranged by book and chapter and learning objectives and projects and some sample enrichment projects. And I'll show you some of those. So we've instead of trying to do standards, some of you know that the beauty of standards is there's so many, especially internationally. In the U.S., the math standards normally get updated every 10 years, and they've been kind of fluctuating around and become political footballs and all this kind of stuff. So we gave up on that, on trying to tie to standards. But so instead we went by topics. So we have a list in the math, in the book, we have a list of topics like this, and we tell you what book and what chapter go with those topics. And so you can kind of get a general idea here that we haven't duplicated all the stuff in each book because they're three relatively fat books, but we've tried to basically create a teacher's index to this so that you can say, oh, I want to teach this, and then you can say, yeah, it's in the geometry book, yeah, it's in the trig book. And we also um, have tried to come up with some assessments and talk about, here's how you can use a specific model to teach this particular thing. So we've tried to make a bit of a cross-reference for you. So you can say, I want to show a student how to compute the volume of a cone, sphere, or cylinder given the radius and height, and show the ratio between the volumes empirically for a set of shapes that have the same height and radius. And that's a model. And so we can say, go and create these models and compute the expected volume from the formula and then measure sand and water and see how that works. So if you have a small class, you can have them actually figure out which size it is they want to print and then go test them. If you have a big class, you could whip out a bunch of these models, which are pretty small and easy to print, and pass them out with some sand or sugar. Well, sugar is a bad idea if you have ants, but salt or sand or something, and and test these out. So we have tried to come up with example assessments, and so you can somewhere between a full lesson plan and nothing at all, so we didn't want to completely drown you. We do have lesson plans for some things. We are kind of currently shopping around for ways to get some support to do more of this. But we do have lesson plans on nonscriptum.com/projects, two distinct sets. One is geometry for teachers of the visually impaired, which preceded the geometry book. It maps to it a little bit. It has some of it sort of maps to the geometry book, some of it maps to the trig book, but they are lesson plans that talk you through with the focus on blind students, but it doesn't really matter, because students are students at some level. And talks you through, how do you want to teach some of these things. We also have a project we did with University of California, Santa Cruz, which was exciting girls about electronics, using the electronics for role play. And so Santa Cruz has a very big website on all this stuff, which we reference in our lesson plans. And our privilege was to try to come up with a very specific scaffolded set of lesson plans using a microbit to first make a magic wand, and then make a familiar in the wizard sense, something that sits on your shoulder and does your bidding. That first had some lights, and the second had some motion and all this kind of stuff. So my little colleague there was one of our students in the pilot, and that's a cat. And the cat, depending on how she moved around, the cat's face would show frowns or smiles or whatever, and the tail would wag, if I recall correctly, depending on what was going on. So that cat was her pride and joy, and she was very pleased with herself. And that she also was featured in Make. So this was also turned into a piece in these lesson plans were a piece in the most recent Make. No, I guess one back Make magazine. So that's kind of fun. And these lesson plans are CC BY, so you can also copy them, do them, whatever you want to do. Just CC BY means you can use them freely, but you need to cite us. We also, if you have access to LinkedIn Learning, what used to be lynda.com, we do have a calculus class there called Assembling Calculus, and that follows the first chunk of the calculus book. And if you like to learn with video instead of with a book, or you want to assign this to students, so this is in LinkedIn Learning, which many universities have subscriptions for all the students. And so if yours has that subscription, the class is called Assembling Calculus. It can be a little hard to find things on LinkedIn Learning because they have an overly helpful AI interface that thinks it knows what you want. But anyway, so the Assembling Calculus class is out there as well. So you can find a lot more of our materials our website is nonscriptum.com. Projects has our lesson plans. Um, Classes has the classes that we have on LinkedIn Learning. We have a whole bunch of excuse me, a whole bunch of classes that are on 3D printing, more focused, but I've sort of focused on the math one here. Um, our emails are there. Me and also Rich will be at LA Maker Fair April 12th. If any of you are in the LA area, we're also going to be doing a whole bunch of other things. And we have a teacher meetup, which we have a link to under events, where we've had a really hard time getting people to come to a Zoom meetup. I don't know what it is, but we hold it every couple of months and see who shows up, and we have a little core group that come, and so it is under the events page on Scriptum. I also want to talk for just a minute. We are in Pasadena, in California. Pasadena and Altadena are the Pasadena Unified School District. And so I want to talk a little bit about being a makerspace in here, just to give you the scale, because you probably haven't been following if you're all over the world. The fires that happened night of January 7th, and subsequently, every one of those red dots is a house that's gone, or a structure that's gone. 8,000 houses, six schools, six public schools, and more, a lot more small private schools. And the greenhouses are things that are somewhat damaged, and the red and the black things are things that are kind of that are still mostly okay. So something like 75 teachers lost homes, and we're all figuring out how to recover. So we work with various Pasadena educational institutions. If any of you are interested in trying to collaborate or do anything, you can talk to me. We're just a tiny outfit, but the Pasadena Education Foundation is the place that is working school recovery to try to figure out how to do that. And it's going to be a very challenging environment for us for quite some time. Um, I live kind of in here somewhere, and there were a lot of really nice little sort of private, kindergarten and preschools and stuff up here, and they're restarting. So it's going to be an interesting time. I think makers have some things to help here, and if you get any good ideas, I'm sure Pasadena Educational Foundation is going to be needing ideas for a while. So check them out. And on that, I will stop, and maybe Rich can join me here too. And do we have any questions here? So how many of you are using our teaching math or thinking about teaching math? Your makerspace folks mostly. So
Um,
go ahead.
well, I was just going to offer, I do an out-of-school summer program, and we are required to do math instruction. And I think this will be an interesting way to do that. We have support from our university makerspace, so I'm looking into the curriculum.
Oh, okay, great. Yeah, and so I'm always happy to correspond, and you know, happy to get emails and happy to chat. Our books are on the Maker Shed, and at the moment they're like when you go into the Maker Shed, they're right there. Which is kind of cool. So Maker's been very supportive of this and trying to tie in real stuff. Did I forget anything, Rich? No, no. So I think the main barrier to adoption has been people are a little afraid of OpenSCAD because it's real coding, but we say, well, you don't have to learn how to code in it. All you have to do is be able to. In our books, we talk through, if you want to have this model instead of this model, change this parameter, and it's also a very good feedback way for kids to learn coding because you type in cube whatever and you hit render and it makes a cube, and so is that feedback that isn't necessarily there if you're going to write a sorting algorithm. I mean, you can write sorting algorithms all day long, but it's hard to tell right away to get that gratification that you've gotten it right, right? And so we have kids that we've taught that we've had used Tinkercad for a while, and then they take another class with us and they learn OpenSCAD, and then they happen to go back in and we get all this whining about, oh, Tinkercad's for babies. I do this project in OpenSCAD. Oh man, so they get used to it. They compete with how to get as many errors as possible. I don't know why they do that, but drives me. Or they figure out ways to make sound. That seems to be the real thing, right? Figure out ways to make something make noise. All right. Well, it's been great to chat with you guys, and hopefully we can stay in touch further and keep fighting the good fight everywhere, right?